Okay, this is the second part of AQA A-level Chemistry. This is the June 2018 paper. And it's the second part of it, starting at question 5. Questions 1 to 4 covered in an earlier video. Okay, so rate of reaction question here. Got bromate ions reacting with bromide in an acid to give us bromine. Okay, series of experiments carried out, set temperature, and results used to deduce the rate equation, which is there. And table 2 shows an incomplete set of results. Use the data from experiment 1 to calculate a value for the rate constant K and give its units. Okay, so what we're going to say is we've got the equation for rate. We've got to rearrange that to give us K. So K is equal to the concentration of bromate. Sorry, K is equal to the rate. Divided by the bromate concentration, multiplied by the bromide concentration, multiplied by the hydrogen ion concentration squared. Okay, now let's use the data from experiment 1 to work out K. So it's a matter of just plugging in the data there. So for experiment 1, you would have the rate is 2.4 times 10 to the minus 2 divided by bromate concentration is 0.1. That's the power of 1. Multiplied by bromide concentration, that's 0.2. Multiplied by the hydrogen ion concentration, 0.3, but that's squared because second order. Okay, put the numbers in there, you will get 13.33 or something. Right, says give to the correct number of significant figures. Well, all of this data is mostly given to 2 sig figs, so we should only give this to 2 sig figs, so you should just write 13. The units, well, we have got on the top line, we've got mole, we've got the units of rate are always mole per decimeter cubed per second. And then we've got 4 terms of concentration on the bottom, because it's bromate to the power 1, bromide to the power 1, hydrogen squared. So that's mole per decimeter cubed to the 4. All right, one of those is going to cancel out, so that's seconds to the minus 1. That cancels out, and that becomes 3 mole dm cubed all of that. So that becomes seconds to the minus 1 over mole 3 dm to the minus 9. Put that all on the top line, so change the signs. Seconds to the minus 1 mole to the minus 3 dm to the power of 9. That's the units there. Okay, now we are probably going to use this value of K later on, so I'll just circle that. The next part of the question, it says complete table 2. Right, now let's look at this. Like, this one is quite easy to fill in because we can see we've kept these are the same, that's the same, but the rate's gone up by a power of 1.5. Now it's directly proportional to the bromate concentration because it's first order, so that's got to go up by 1.5, so that becomes 0.15. The others, there aren't any quick ways of doing it really, and probably the safest thing is to just put this value of K into the rate equation to work out rate for that one there. So that gives you a value. You put your numbers in there, you get 0.26 for that. Rearrange to get H plus concentration for this last one, so you're going to have to do H plus squared is equal to rate over K, which we worked out as 13.33, divided by the bromate concentration, which is 0.1, multiplied by the bromide concentration, which is also 0.1. Find out H squared and square root it, and you should get a value there of 0.45. So That's probably the easiest way of doing those last two, is just to substitute the numbers into the equation. Okay, so that's that question done. The next question is carries on. This is an Arrhenius question. Okay, so what they did here was the same reaction, and we want to find out the activation energy using the Arrhenius equation. So they used identical, so they kept the concentrations of everything the same, and they only changed the temperature. And they took the time taken for a fixed amount of bromine. They didn't say how they did that. We don't really care how they did it. The time t for a fixed amount of bromine to form. And of course, rate there is going to be proportional to 1 over the time taken. So that's what they're finding out here. That's the rate. This is the temperature in Kelvin. And they worked out the reciprocal of the temperature. We'll see why in a minute. Right, so it gives you the Arrhenius equation. Okay, here. So there's the Arrhenius equation. The rate constant is directly proportional to 1 over t if you keep the concentration of everything the same for every experiment. That's what they've done. So they're going to use this. They're going to make this fit into, y equals to mx plus c. And then if you plot 1 over t, ln of 1 over t on the y-axis against 1 over the temperature on the x-axis, you're going to have an intercept, which we don't care about that, but the gradient is going to be equal to minus the activation energy over the gas constant R. So, right, the first thing you have to do is complete table 2, so that is really easy. You just put, here you press on the ln button on your calculator, ln 1 over of that, and that should give you a value of minus 3.29. Quick common sense check, it sort of fits in the pattern there. Reciprocal of the temperature, so that's 1 over 302. On your calculator, 3.31 times 10 to the minus 3 there, and that fits into the pattern. Right, now, so they're going to ask us to plot that the 1 over t on the y-axis and 1 over the temperature, ln 1 over t on the y-axis, 1 over absolute temperature on there. Okay, so if you choose that scale, it fits exactly on the graph paper. And if you looked in the mark scheme, if you don't use that scale, a lot of people I'm using 5 big squares to be a unit of 1 on this axis. Okay, 5 big squares is 1. A lot of people used 5 big squares to be unit 2, and they knocked a mark off that for not using the graph paper. And it's not a particularly nice scale they've chosen for you to plot. I plotted it there, drawn a line of best fit. And what we've got to do now is we have got to find out the activation energy. So what we've got to do is we have got to find out the gradient of that line, because EA again is equal to minus m over R. Sorry, beg your pardon. M is equal to minus EA over R. Rearrange that, we get EA is equal to minus M multiplied by R. Now you can see the gradient of this line here is negative, which is good because that means that minus the gradient times R is going to be positive. The activation energy EA is going to be positive, it's got to be positive. Okay, right, let's draw. So I would always suggest that you draw the construction lines when you're doing a gradient. It's not like it's GCSE math, but it's very easy to make mistakes on it. So I'm going to use that line there, this triangle there, to work out the gradient. So it's the change in the y-axis. So here we've got, it's going from -4 minus minus, and that's 2.75 about there, okay? Minus 2.75. So the change in the y-axis is equal to minus 1.80. Let's do the change in the x-axis here. So here we have got 3.5 times 10 to the minus 3 here, and here's 3.2 times 10 to the minus 3. So that is going to be equal to 0.25, sorry, 2.75 times 10 to the minus 4. So that is actually not 3.2, it's 3.275, that line there, yeah. That's 3.275 about there. Okay, so 2.75 times 10 to the minus 4. So let's work out the gradient then. So the gradient m, change in the y, change in the x. So that's going to be 1.8 minus 1.8 divided by 2.75 times 10 to the minus 4. And that gives a value of 6,545. Now we've got to work out, we've got m, we need to work out EA. So EA is equal to m times r, 6545 multiplied by 38.31. Now this is important because the units of r are 8.31 joules per mole per Kelvin. So that means our value of EA is going to be in joules. Okay, so let's do that. So 6,545 times by 8.31 gives you 54,400 and something. Okay, that's the three significant figures. That's joules per mole. Convert to kilojoules, 54.4 kilojoules per mole. Okay, so that's the sort of thing you've got to practice, really. It's quite time consuming, and you don't want to spend ages carefully plotting a graph. You want to be able to do it quickly, working out the gradient. I strongly recommend, as I say, always write down the construction lines, write down the numbers like I've done here. Save making sort of careless mistakes. Very easy to do. Okay, so that's the end of that question. Right, here the usual question about benzene, very common question, you know, where you look at the thermochemical data for the evidence that there's electron delocalization because it's more stable than it should be. Okay, first of all, explain the bonding in and the shape of a benzene. So the bonding and the shape of a benzene molecule. We'll do that bit first before we talk about the energy. Okay, so what you're going to say is you have got you've got a sigma bonded 6 carbons, okay, and you also have there you have the p or p electrons. There's 6 lots of p electrons not involved in the sigma bonding, and they overlap to form the pi delocalized electron system. So that's the bonding. How about the shape? Well, the each carbon is bonded to 3 other things, okay, and there's no lone pairs there. So that means the bond angle is 120 degrees. 3 bonding pairs, no lone pairs, 120 degrees. And 120 degrees is the internal angle of a regular hexagon. So they're all 120 degrees, and they're arranged in the carbons are in a regular hexagon. And you have an area of electrons, delocalized pi electrons, above and below the plane of the ring. That's all you really need to say there. You don't need to go any more technical than that. Right, now compare the stability. So what you need to say is there are, right, with cyclohexene, when you hydrogenate one double bond, you get minus 120 kilojoules per mole out. You would expect for benzene to get 3 times that value if it was an alternate single bond double bond structure. If it was like that, you'd expect 3 times that value, so that would be equal to minus 360. You don't get as much as that, you get a lot less. So the benzene is stabilized by, and you can work out the number of kilojoules, so it's 360 minus 208. It's stabilized by 152 kilojoules per mole, and that is due to the electron delocalization. And I don't know in the mark scheme for this whether you have to calculate the number, but in past mark schemes you did have to calculate the number 152 to get the maximum mark, so I would do that. Okay, right, so that's a fairly standard question on benzene. Recall really. This one's a little bit harder, a little bit more unusual. Okay, the enthalpy of hydrogenation of cyclohexadiene, so when you've got 2, is not exactly double that cyclohexene. So what they're talking about here is this structure, alternate single double bond. Okay, and we can guess that because you're going to have delocalized, you've got unpaired p electrons here and here and here and here, they will delocalize. So it won't really be alternate single double bonds. Now, for cyclohexene, when there's one double bond, it's minus 120. You would expect this to be minus 240. Okay. Now we said when you have the benzene, the full thing, that's stabilized, we worked out, by 152 kilojoules per mole. So this is like 2/3 of a benzene ring, isn't it? So I suppose, or half, yeah, because it's about half of the between, and it doesn't actually matter whether so I suppose it's like half the benzene ring is delocalized. So let's say you get half of that stabilized. It was approximately 125 stabilization. So this is going to be not as big as 240. It's going to be less by 125, which makes it 115, I think, isn't it? 240 minus 125, yeah, 115 kilojoules per mole. So you wouldn't get actually you wouldn't get as much out as 240. So half of 152 is not 125, it is about 75, isn't it? That's what I'm talking about. Right, so 240 minus 75 gives you, say, what's that? 100 and 165. Okay, so I would suggest a value, I'd say minus 165 kilojoules per mole. And I think if you look in the mark scheme, they give you anything which is less than that. So they give you anything from minus 239 to anything which is a tiny bit more than that, 121. So any value between those, they're very generous there. They let you have. So it's a bit, it's stabilized due to electron delocalization. So you don't get as much energy out as you would expect when you break the double bonds and hydrogenate it. The justification, of course, is just that justification is just the electrons are delocalized because you've got, I would say you've got alternate single double bonds, so the p electrons can overlap. Right, question on acyl chlorides here now. So they're useful in organic synthesis. They react with aromatic compounds and with alcohols. Right, so propanoyl chloride here will react with benzene in the presence of the aluminium chloride catalyst in electrophilic substitution reaction. Give an equation for the reaction of propanoyl chloride to form the electrophile. Okay, so if you remember what happens here is, so I'll write the equation first. I'll write it like that. So if you remember, the aluminium chloride actually takes off this chlorine with those two electrons, and that is going to generate, you wouldn't leave that in obviously, your answer, that is going to generate, that is a positive charge, and that's the electrophile, and you would get aluminium Cl4 minus. Okay, so I need to put plus AlCl3 there. That's the equation for the generation of the electrophile. And an outline of the mechanism, well, that's a straightforward electrophilic substitution. So straightforward recall. Let's just write it down. So you're going to have your benzene ring. I do the benzene ring nice and big because they are quite picky about where the arrows, you know, curly arrows come from and stuff. Here is your electrophile. I'll draw it backwards. Okay, so a pair of electrons come out of the benzene, the delocalized system, and form a bond to that carbon. Draw the intermediate. This is where it's important to draw a nice big benzene ring. So we've now got our acyl group stuck onto the benzene ring. And we remind ourselves that there's also a hydrogen stuck there. So we actually draw a hydrogen on there usually. And the delocalized system is now broken. Now it's broken from that carbon to that carbon, so that you want your sort of circle to go around like that from those places, and they're particular about that. And of course, this is going to have a positive charge, which is spread out through the whole delocalized system. And then the final step in the mechanism is the pair of electrons go back in the delocalized system there. So you're going to form the product. And you'll also get a proton. Okay, so that is, and the name of the mechanism, oh, they don't ask the name, they quite often do, but they're not asking for it there. It's just, yeah, so that's 4 marks, 1 for the equation and 3 for the mechanism probably. Okay, right, the organic product produced in there can be converted to the alcohol shown. Okay, right, let's just, before we answer the question, let's just think what's happened there. So look what's happened. You've got a ketone group, and we have turned it into a secondary alcohol there. It's a reduction. Okay, and the Alaska slate, remember it's a hydride ion from, yeah, it's a nucleophilic addition reaction. So that's going to go onto there, and then that goes onto there. Just to, they haven't asked us that, but just to remind you. Right, the name for that, well, first if you just look at this without the bend, you've got propan 1-ol. But also stuck onto propan 1-ol, you've got this benzene ring, and it's called the phenyl, so you call it 1-phenyl. It's on carbon number 1, 1-phenyl propan 1-ol. Now the reagent needed for that, well, we said it's a reduction and it's nucleophilic addition, hydride ion, but that's not the reagent. The reagent is, of course, sodium borohydride, NaBH4. That's basically essentially the hydride ions, a carrier for the hydride ion, and the mechanism is nucleophilic addition. Nucleophilic because the H- is attracted to the delta positive carbon on the carbonyl, and addition because you end up breaking a double bond. Okay, question 7.3. The alcohol in 7.2 reacts with ethanol chloride to form an ester. Okay, so whenever you react an alcohol with an ester, alcohol with an acyl chloride. So I'll just write down, I'm not going to, there's propanol chloride, and here's our alcohol. It's nucleophilic addition elimination, isn't it? Right, so that's going to go onto there. Right, you end up breaking the pi bond before that reforms, but you lose Cl minus and you lose H plus, and so you get HCl gas formed, and that's usually described as looking like steamy fumes. Okay, so the observation is the steamy fumes of HCl. Steamy fumes, that's that. The name of the mechanism is nucleophilic addition followed by elimination. They don't ask you to draw that mechanism there, which is usually like a 4 or 5 mark question. And the structure of the ester, well, it's going to the alcohol is going to react with ethanol chloride, right? So let's just grab that alcohol, right? So I'm going to just, right. There's the alcohol. And we want that to react with ethanol chloride. Let's rub this out here. There's our alcohol. Right, ethanol chloride looks like this. Yeah, okay, so that lone pair is going to attack onto there, right? So let's draw the structure of the ester. The ester is going to look, I'll just draw it onto there, so get rid of that H, you're going to lose that, and you're going to lose, and then the carbonyl from the ethanol chloride, that's ethanol chloride, so that's what it would look like. Okay, that's the structure of the ester. Right, onto biochemistry, and this is showing a protein. Okay, use your data booklet to help you answer this question about amino acids. Shows part of 2 polypeptide chains in a beta pleated sheet of a protein. Okay, the polypeptide chains are held together by hydrogen bonding. Explain how hydrogen bonds form. Well, that's really just a year 12 question on intermolecular forces. You would say, you would say, so you're looking for 2 marks, you'd say lone pair on the carbonyl oxygen, or on the lone pair on the carbonyl oxygen is attracted to the H attached to the nitrogen, which has a partial positive charge on it. Rather than write delta positive, write partial positive charge on the nitrogen, on the hydrogen, because the nitrogen is much more electronegative, and so you get a hydrogen bond forming. Right, now some amino acids, a different type of bond can be formed between 2 different polypeptide chains with the amino acid cysteine. Okay, so if you look on your data sheet, you'll see the amino acid cysteine has got, that group, and it's got the amine group here, and the R group has got an SH group on it. Okay, and what happens is, you get, so this is this carbon here, okay, on the cysteine, and so you have the R group, you're going to have CH2SH. You've got the same on this one. This is this carbon again here, so you're going to have CH2SH. And what happens is you lose those 2 hydrogens there. So it's actually a reduction reaction, so an oxidation reaction. You're removing hydrogens, and you form a new covalent bond between the 2 sulfurs. It's called a disulfide bridge, and it's a covalent bond. Okay, that's the 1 mark there. Okay, and the structure of cysteine is on your it is on your data sheet. Okay, the type of bond in 8.2, this the cysteine, the disulfide bridge, influences the 3-dimensional structure of the protein. This type of protein structure, they're looking, the answer there is tertiary structure. The beta pleated sheet or the alpha helix is called the secondary structure, and any other higher orders of how that's arranged with covalent bonds, whatever, is called the tertiary structure. Now draw the zwitterine of a dipeptide formed by alanine and serine. Okay, so you've got alanine and serine are both on your data sheets. So let's draw, I'm going to draw alanine. CH3 is the R group in alanine. You've got always, everything's got H, and then you've got the amino group here. And then you want for serine is very similar to that, but the only difference is, actually you've got the, so all amino acids all have that structure, and the R group for serine has actually got an alcohol, and it's CH2OH. Right, how are they going to form a dipeptide? Right, you're going to lose water there. Do that, get rid of that. And so the new bond is formed there. That's the peptide link. Now, it's important to notice here that I have drawn serine with the free, sorry, I've drawn alanine with the free NH2 group and serine with the free COOH group. It could equally well be the other way around. There are 2 different dipeptides of alanine and serine. Just swap them about and you can draw either one. But here it just say there's zwitterine form. Okay, so we need to protonate any NH2 group, so we protonate that. Incidentally, that will not protonate. That nitrogen there is not a good base. We don't need to know that, but it doesn't get protonated. It's not a good base because it's next door to this carbonyl group actually, which withdraws electrons from it. But don't worry, that's that. And we need to deprotonate the, protonate the NH2, protonate the carboxylic acid, deprotonate the carboxylic acid, so that's O minus. That's the zwitterine form of one of the 2 dipeptides. Yeah, the other dipeptide, you could just swap those 2 R groups about. That's what the formula of the other dipeptide would be. Okay, on to DNA. Okay, so we have got, you biology, you're probably very familiar with this. A, C, G, T represent the 4 bases. Okay, and so we've got to show the complementary bases. Right, now A always hydrogen bonds to a T on the other side. That's always to, C is always to a G. That's obviously going to be a C, that's going to be an A, and that's going to be a G. So that's T, G, C, A, G. Now, a little bit harder, it says here, deduce the total number of hydrogen bonds formed between these 2 5 bases. Well, TA pairs, and we've got the TA pairs there, they have 2 H bonds each. So we've got 2 times, we've got 4 from that. GC pairs, they actually form 3 hydrogen bonds, which you should know. So that's going to be 3 of them, plus 3 times 3 is 9. So that's going to be 13 is the right answer. That's the number of hydrogen bonds. So GC forms 3 hydrogen bonds, TA only 2. Okay, right, base A, now these little bits here, I've just snipped out of the data sheet that you get. Okay, so you get all of these. So there's the bases AGCT, and that is deoxyribose, the sugar. Base A is a nucleotide. Okay, a nucleotide contains a 2-deoxyribose molecule. Okay, and it's always got the base, and you need to know the base is always attached. So if you customize your sheet, it's the base is always attached with those ends there. It's not really asking us that, but it's worthwhile remembering that. And it always attaches there. So what happens is you have the NH you're going to lose water, and so you end up with the nitrogen directly bonded to the carbon there. Sticking it there. Right, so it says represent the base by the letter A, so I'm just going to put A there and put all the other bits on the molecule. So we need to put on, with these, normally you don't put H's on skeletal formulae, but you do on these. So it's H there, H, 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 O, H, H, and here we have got CH2 and an O, and that is attached to the phosphate group. So you've got phosphorus forms 5 bonds. You have a double bond, you should know this to an oxygen. You have a single bond to an oxygen that's negatively charged, and then you have another oxygen, and that is attached to the next nucleotide. That actually, this one here, okay, so just do that blue there, that attaches down there to the next one. Right, so it's important that you get your phosphate in the right place. This is usually called the 5' carbon, that one there, and this one here is called the 3' carbon. Now in the nucleotide, the phosphate is always attached to the 5' carbon, but that when it polymerizes, you know, this then attaches to the 3' carbon on the next one. But the individual monomer, the nucleotide, the phosphate is always on, there's the monomer, the nucleotide, it's always on the 5' carbon. And don't forget to stick that, to draw that carbon in there. Okay, so if you just drew that straight to an oxygen, you lose a mark for that. Okay, infrared spectroscopy, and again, I've just pulled a bit of the data sheet out there. We might use some of that. Incidentally, all these ones here, I always tell people to ignore them, those two, because they're actually in the fingerprint region, yeah? So you can't really say what's what at all there, okay? The fingerprint region is everything, you know, all that's the fingerprint region, isn't it? So we don't really look at that. Okay, so we've got a primary amine, a tertiary amine, and a nitrile, and you've got to work out, right? So I'd home in on the nitrile first of all. That's probably the easiest thing to do, it's because it's got that group in it, and here you've got an absorbance about 2,200 per centimeters. So you can see that has got to be the nitrile. That peak there is very characteristic, and it's always that shape as well. It's also quite sharp. Now, primary amines have got hydrogens attached to the nitrogen, whereas a tertiary amine, nitrogen forms 3 bonds, it's bonded to 3 different carbons, yeah? So there's no hydrogen attached to it. And here, look, you get a very characteristic bond. It's in a similar place where the alcohol OH one is. So the primary amine is going to have a bond in that region there. And look, this one has got a hydrogen attached to a nitrogen there. So that's definitely the primary amine. So process of elimination, this one must be the tertiary amine. There's nothing particularly in that spectrum to show that it is a tertiary amine, but just process of elimination. That's, the other two are fairly obvious. Okay. Right. Now, there are 3 secondary amines that contain 4 carbon atoms per molecule. So don't forget, a secondary amine has got 2 carbons attached to the nitrogen. All right, so we've got 4 carbons. So we could have that one. Let's say 2 ethyl groups attached. The other obvious one is we could have 1 methyl and a propyl. And the third one's not quite so obvious. I think you've got to put a branch in the propyl. So it would be like with a methyl there. And they've asked that question quite a lot, actually, in various guises, you know, 4 carbons. And, you know, I think there was a 13. See, it said this one will give 3 signals. No, yeah, 3 signals on 13C, because these 2 carbons are exactly the same here. That's a previous similar sort of thing. Anyway, it does ask for a skeletal formula, so we must draw a skeletal. So we're going to put N there. All right, that's an ethyl group. That's 1 carbon there, 1 carbon there. so that you don't have to put the H on the nitrogen. This one you can have, that's the methyl group, and that is the propyl group. 1, 2, 3 carbons, and this one we want the skeletal, that will be there, and then you're going to have like that. Okay, that's how that one looks. So there's your secondary amines. Right, primary amines can be prepared by the reaction of halogenoalkanes with ammonia or by the reduction of nitriles. Okay, so justify the statement it's better to prepare primary amines from nitriles rather than haloalkanes. Okay, right, now if you do it from a nitrile, you reduce it, so you can add hydrogen nickel catalyst and you will get that. Now the advantage of that is you only get, that's the only product. Now if you remember, if you do it by the other method, by haloalkane plus I'll just draw bromoalkane plus ammonia, it's a nucleophilic substitution reaction. So what happens is that lone pair attacks there because it's delta positive, and you lose the bromine, and you will get an intermediate, but you will get that. But the trouble is that this has got a lone pair on that, so that's a nucleophile as well as the ammonia. So that this thing can react with another CH3Br, and you can end up getting, essentially you're going to replace another hydrogen. So so you CH3 there, get rid of that, sorry. You'll end up getting that, and of course that is also a nucleophile, so you can replace another one. So you get a tertiary amine, and you can even then end up, essentially you replace the lone pair and you can end up with a quaternary ammonium salt. So you with this method, you can get a mixture of primary, secondary, tertiary, and even quaternary ammonium salt. Whereas with the other one, the reduction of the nitrile, you only get one product. Okay. So draw the structure of a primary amine with 4 carbon atoms that cannot be formed from a nitrile. Now, nitriles can only go on the end of molecules, because you need 3 bonds to form that. Okay, so yeah, you can turn that into, you can reduce that. But saying if we wanted, if the amine is in the middle, so saying if you had an NH2 group there, don't forget that's still a primary amine. It's not like an alcohol where it would be a secondary alcohol. That's a primary amine. Now that you can't have, if it was made from nitrile, it would be from that, and that's impossible because that carbon would be forming 6 bonds, wouldn't it? Okay, so that's not allowed. 5 bonds. Use that one there. Okay, so you can't have a nitrile in the middle of a chain there. That's impossible. Okay, so primary amine that can't be drawn from that. Let's draw CH3, CH2, CH, NH2, CH3. That you can't make that from a nitrile. Okay, now it's about the basic property of amines. So a student drops a few drops of propylamine in water. All right, give me a look through the equation that occurs. Okay, so propylamine, CH3, CH2, CH2, NH2. Let's put that to remind ourselves it's a base. That's going to accept a proton from the water. It's not a strong base, so it's a reversible reaction, and so you're going to get CH2, CH2, NH3 plus, and you're going to get OH minus ions. What would happen when you add a universal indicator? Well, you've got a bit of OH minus in there, so it's probably going to be like pH 11, 12, something like that. So it would go blue, orange, so we go green from neutral to blue. If you look in the mark scheme, they let you get away with purple there. which is also alkaline color. Okay. Phenylamine can be prepared by reducing nitrobenzene. So here, if we've got, you've got NO2 on there, that's the usual way of making it. So you reduce that by getting rid of the oxygens, replacing them with hydrogens. So you get NH2. That's what we've got to do. Right, give an equation for the reduction. So I'm going to write down that as C6H5NO2. Don't forget it's H5 because you don't have a hydrogen on that carbon there. And we're going to turn it into C6H5NH2. And we need some hydrogen. That says always, when we're doing these, we always write down, if you like, that's an H plus ion with an electron. Okay, or hydrogen atom. So what we're going to do, those oxygens here, the two oxygens end up as water, so we're going to get 2 H2O. So how many extra hydrogens have we got? We've got 4 there, and we've got 2 there, so we need 6 of those to balance it. Okay. Explain why an aqueous solution is obtained in this reduction, even though phenylamine is insoluble in water. Well, phenylamine is insoluble in water because it's not charged, but there's acid about here. Okay, it's got hydrochloric acid. What's that going to do? It's going to protonate that, even though this phenylamine is a very weak base because you've got excessive hydrochloric acid, concentrated hydrochloric acid. So that's going to be NH3, and that's going to be plus. And that's soluble because it is charged. It's an ion, and ionic substances tend to dissolve well in water. And so, yeah, most amines are much more soluble in acid solution than in neutral solution because you have protonated it and made it charged. Right. So this is by isomers of the formula C6H16N2. Right, so there's one, and it's quite useful though. We can see from this that there's no double bonds in that. It's saturated. It's not always obvious to tell when you've got nitrogen in there from the ratio of the carbons to hydrogens. No double bonds there. So the number of peaks in that spectrum, in the C13 spectrum of that isomer, well, we are going to have they're identical. They're the same as each other. 1, they're the same. 2, 3. That is not the same as that one, so you'll get 4 peaks. Okay, the splitting pattern of A, well, it's going to be a triplet, isn't it? Because the one next door to it, this one has got 2 hydrogens, the N+1 rule, so that's why it will be a triplet. Okay. Now draw the structure of the eyes of the C6H16N2 used to make nylon 6,6. That's kind of a straightforward recall question. It's 1,6-diaminohexane, so it's basically, you've got NH2 at each end, and you've got 6 carbons, so 6 of those NH2. Okay, that would be the, and you can draw, if you wanted to, you could draw a skeletal version of that, but okay, that's what it is, and that's just, as I say, a recall question. You just got to know that. Okay, draw the structure of the isomer of C6H16N2 that contains 2 primary amine groups, and it's only got 2 peaks, so we're going to have a lot of sort of symmetry going on here. Okay, so let's think. So we're probably going to have an NH2 at each end, and we've got 6 carbons to think about. So I think if you get like that, let's put just for the skeleton first, put 2 carbons there. We've got 2 primary amines. We've got 4 left over, so we could have 4 methyl groups here. And that would only give us 2 peaks because all those methyls are all the same as each other. And these 2 carbons, they're the same as each other because it's symmetrical. And so you'd get just 2 peaks in the spectrum there. Right, I think we're getting to the end of this paper now. Draw the structure of the isomer of C6 that contains 2 tertiary amine groups, and it's only got 2 peaks in its spectrum. Okay, right, now it's got to be a tertiary amine. Oh, I think I've drawn that. 2 primary amine groups and then 2 peaks. Okay. Structure contains 2 tertiary amine groups and it's only got 2 peaks. So tertiary, no, right. So you could have, let's think, it's got to have, let's say it's got that. Now we have got 6, so we've got 5 other things to think about. So, right, it couldn't be that because they're not going to be, if I did that, CH3, 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 right, we're missing a carbon atom, aren't we? We've got 5. So what we need to do is just put CH2, CH2 in there. And that will work because once again we've got symmetry. These two are the same as each other, and then all those methyls are all exactly the same as each other. So that's the answer to that one. Right, now 11, I think that is the end of the paper.